Let's look at algebraic limits with rationalizing an expression. Algebraic limits, rationalizing square roots. Okay. So in your algebra classes, you probably have rationalized denominators before. It's the process of getting rid of a square root in a denominator. Now, what we're going to look at, though, is rationalizing square roots with regard to limits. So, for example, let's say I want to consider the limit as x approaches 0 of this rational expression, the square root of 3 plus x minus the square root of 3 minus x all over x. And so what you see here is if you try to evaluate the limit by direct substitution, you would be dividing, dividing by 0. So clearly that's not going to work. So what we're going to try to do is something that's not totally obvious, but this is a common technique. We're going to try to get rid of the square roots on the top. Square roots often result in irrational numbers. Getting rid of the square roots turns them rational. So that's called rationalizing the square roots. So what we'll do here is we'll multiply the top and the bottom by the same thing as the numerator here, but with the opposite sign. So instead of a minus here, we'll multiply by the same expression with a plus, and that's called the conjugate. The conjugate. So I'll write it out in a second. So you're going to multiply by the square root of 3 plus x plus the square root of 3 minus x. And so this is what we call the conjugate, okay? It's a useful technique. Now, if I want the green fraction to equal 1, I have to multiply the denominator, x, by the same thing. So this will be square root of 3 plus x plus the square root of 3 minus x, okay? And now, all that's left to do is to multiply this mess out. So this will equal the limit. We're going to take this binomial of square roots and multiply it by this binomial of square roots. The good news is they're conjugates, okay? I'm going to erase this so I have some space here. They're conjugates. When you multiply conjugates together, all the stuff in the middle cancels. So what I mean by that is I'll multiply this square root by this square root. When you multiply a square root by itself, the square root goes away, so all we have is 3 plus x remaining from that product. Then typically you would multiply this first term by the last term here, and then the last term by the first term here. But you might notice that you'll get the square root of 3 plus x times 3 minus x, positive here. And if you multiply the two middle terms, you'll have a negative square root 3 plus x, 3 minus x. And so you get the same thing twice, one's positive and one's negative, which adds to 0. So because these are conjugates, we don't even have to bother with that. We know it's always going to add to 0 for those terms. So all that remains is multiplying the second term here by the second term here. And it's a negative times a positive, so we've got minus the square root of 3 minus x times the square root of 3 minus x. A square root times itself just results in the radicand within the square root. No more square roots on top. We've rationalized the numerator. Then on the bottom, we are not trying to fix anything on the bottom. We're not trying to rationalize anything. So rather than distributing this out, I'm just going to leave it as x times the binomial of square roots. So the square root of 3 plus x plus the square root of 3 minus x. We don't want to distribute there. Remember, we're taking the limit as x goes to 0. So what we're hoping will happen algebraically is we're hoping this x denominator will cancel, because then we won't be dividing by 0. And so what we see happens here is this is the limit. If I distribute my negative here, I get 3 minus 3, which is 0. And I get x plus x, so that's 2x. So I get 2x over x times that same binomial. And rather than write it all out, I'll leave it like that. And now the x divided by x is 1, so now I can cancel my x's. And finally, I have the limit as x approaches 0 of 2 over, no x, and I've got the square root of 3 plus x plus the square root of 3 minus x. And all that remains now, because I'm not dividing by x's, I can do direct substitution to see that this equals 2 over, well, I'll plug in 0 for x, I get the square root of 3. Sorry, I copied this wrong. This should be a plus on the bottom. I get the square root of 3 plus the square root of 3 minus 0 is also the square root of 3. So I get square root of 3 plus the square root of 3. 1 square root of 3 plus 1 square root of 3 is 2 square roots of 3. And then, since this is multiplication on the bottom, I can cancel my 2's. And so I get 1 over the square root of 3, which is perfectly fine. But if you want to rationalize the denominator because there's a square root, the way to do that is to multiply by the square root of 3 over the square root of 3. Some basic algebra there. And you end up with the square root of 3 on top. And on the bottom, you get the square root of 9, which is just 3. So the limit as x approaches 0 of this sort of complex rational expression with square roots can't be evaluated by direct substitution, but if we rationalize the square root portion, it allowed us to cancel that x on the bottom, thus calculating the resulting limit by direct substitution with one more little rationalization here. So that's a pretty basic example of evaluating limits using by rationalization.